All right, folks, welcome to this live virtual weather and climate office hour. This one's going to focus mainly on the now historic, in many cases, snow drought and record warm start to, uh, doesn't feel a lot like winter, but in fact, that is what the astronomical and calendar tell us that it is right now as we're here on the February 9th. Talk about where we are now, and then really focus on the major pattern change that I'm anticipating that is pretty clearly on our doorstep with a pretty dramatic shift from literally record warm temperatures and very dry air, even through today in many places, to rain and wind tomorrow for Central California, and a general switch to a wetter, cooler pattern over the American West over the next couple of weeks, which will bring at least a temporary reprieve from the warm and dry. And while it's not going to erase the enormous accumulated snow deficits in the mountains this winter, it might bring us away from record low territory, at least in some areas. So some good news there, and probably will bolster the ski season. How much it's going to save the snowpack from a water supply and subsequent wildfire perspective is a bit of a different story, but there is some good ski industry news to come out of the next couple of weeks throughout really most of the West. And some of that will trickle down, literally in this case, to the hydrology and the ecology of the region as well. So I want to talk about that today. And at the end, as I always do, I'll try and take some questions live from the audience. Please try to keep them relatively on topic and generally associated with those topics I just mentioned in this introduction. Just a reminder that this channel is sponsored by Reask, a climate tech company that's helping to rethink extreme weather risk in a warming world. So it's been really warm, and I don't even need to be specific about where you are listening when I say that, as long as you're in the western third of the US. It's been really cold in the eastern US in recent weeks. In fact, as has been discussed extensively in the news, there are some parts in the eastern US that have seen their coldest week or 2-week period in several decades. However, notably, as far as I'm aware, none of these locations have seen their coldest week or 2-week period on record, or coldest month on record. In fact, January wasn't even that remarkably cold from a month-long perspective, although it got very cold at the end in the eastern US. I've been speaking with a lot of journalists today and last week about the extreme dipole in temperature, this really warm west and really cold east, but really emphasizing that as cold as they have been, the Arctic blast in the east has not been nearly so anomalous on the cold side of the temperature distribution as has the extreme and, yes, record-breaking warmth all throughout the west on the warm side of the temperature distribution. So although it is extremely warm in the west and extremely cold in the east, they're not equal and opposite. The relative degree to which it is warmer than average is much greater in the west than the relative degree to which it is cooler than average in the east. Ironically, though, some of the short-term societal effects of the extreme cold in the east have probably been higher impact than has the much more meteorologically anomalous warmth in the west, at least in the short term. And that's because we've seen really disruptive and even destructive ice storms associated with this Arctic blast, and a lot of snow, which has not melted very easily in places that rarely see accumulating snow at all. So that's been very disruptive for travel, for electrical infrastructure, for day-to-day life. And the death toll is above 100 from this extreme cold in the east because, unfortunately, there were a number of incidents involving car crashes and other kinds of accidents, as well as acute hypothermia. So it's not to diminish the impacts of the extreme cold weather in the east, but it's to emphasize that we often hear that, well, it's cold in one place and it's warm in another place and it all evens out. I assure you, I've done the math and it doesn't even out. It's the warmest warms are definitely outpacing those coldest colds. And in fact, when we look at this in a systematic way, nationally and internationally, we see that the rate of record warmth outpaces the rate of record cold in recent years by anywhere from a 2-to-1 to a 4-to-1 ratio. So let's just call it 3-to-1 on average, meaning there are 3 times as many record high temperatures as record low temperatures once you zoom out far enough. And of course, you would expect in a climate that wasn't changing that you get roughly the same rate of record warm and record cold. Occasionally, you still get records on both ends of the spectrum, but you'd expect those rates to be about the same if the climate weren't changing. If the climate were cooling, you can guess what we might see. We would see an increased ratio of cold records relative to warm records. If the climate were cooling, we'd still get occasional record warmth, but it would be greatly outpaced by record cold. But of course, that's not what we're seeing. What we're seeing is a rate of record high temperatures that are greatly outpacing record cold, which is itself a clear signature of warming in the long run. And so here in the West, we've been under the warm side of this warm west, cool east temperature dipole pattern across North America. And there have been other similar regions around the world that have seen other dipoles right now. Northern Africa, for example, on the warm side of a dipole, that has brought very cold, extremely cold temperatures to Central Europe, including, unfortunately, to Ukraine right now, where there has been mass power outages and lack of heating due to the ongoing war there, and also to Central Europe, where there's been pretty significant disruption in Germany and other adjacent countries. Again, when there's been temporary power outages amid the extreme cold, it's been a big problem. This really highly amplified pattern, although I'm not going to emphasize on the global effects today, is also having a major consequence for Southern Europe as well. And in Portugal and Spain in particular, there has been an almost unbelievable, I mean, literally I had to verify this morning that the numbers were correct, because the numbers are so extreme that it is almost hard to believe meteorologically. Very intense precipitation event that has led to catastrophic and historic flooding. And I'm being vague about Portugal and Spain because it's actually quite widespread throughout both countries right now, and it is ongoing, continuing to get worse. The numbers are so large, in fact, from this persistent stuck pattern that's allowed for this persistent series of warm, wet, and unstable atmospheric rivers to affect much of the western half of the Iberian Peninsula. That I think it probably, just looking at the numbers today, it's fair to call this the kind of the arc storm-like scenario for the Iberian Peninsula, and it is roughly apples to apples. And we've talked about the arc storm scenario for California in the past, this hypothetical extreme flood scenario, winter storm, and severe flood scenario on a statewide basis. It does make sense to talk about these things in the same breath because, of course, the Western Mediterranean has, well, as you'd expect, a Mediterranean climate, much as California does. So wet winter, relatively dry summer. It's a little less accentuated. You do get more thunderstorm downpours in summer across much of the Mediterranean than you do in California, especially the Western and Northern Mediterranean. The Eastern Mediterranean probably has more of a California-like dry summer where it really doesn't rain. But anyway, it's a comparable climate. California and Spain, Portugal all have so-called Mediterranean climates. And so it's the same general mechanism where you might expect to see a very severe flood scenario for California, a very prolonged, very intense series of atmospheric river type storms bringing one wallop after another. And that's exactly what we've been seeing, especially in the mountainous terrain on the Iberian Peninsula. So all of this is part of a very persistent global pattern of ridges and troughs that have been stuck in place. We can call it warm west, cool east in the continental US. We can call it the warm Arctic, cold continent pattern in the northern hemisphere. There's some other stuff going on there as well. And of course, all of this is occurring in the context of a climate that is significantly warmer than it used to be, with warmer air in most places at any given moment, and also moister air in places where the storm track is currently active. So it's been quite a wild 30 to 60 day period in the northern hemisphere weather-wise. Also worth noting, it's been pretty wild in the southern hemisphere too, and Australia, particularly southern and southeastern Australia, saw a really serious wildfire outbreak back in January, which led to significant structural loss amid a major lightning bust wildfire events. So California's familiar with these. 2020, think about all those dry lightning strikes that ignited all of those destructive fires at once. Similar in Australia last month. Of course, it's their summer in January, so it is comparable to August 2020 in California, the scenario that unfolded down there, and then was followed by record-breaking extreme heat. 50 degree centigrade heat, the hottest temperatures ever observed in some parts of Australia immediately following that lightning outbreak. So again, wonder if that sounds familiar. So it's been another extraordinary weather period globally as well, just to give the big picture. Right now, the eastern U.S. is sort of in its final stages of the extreme cold, and that's going to be fading rapidly as the pattern flips over continental U.S. and North America to from warm west, cool east to cooler west and warmer east. Not particularly remarkable in either respect, but the more notable thing will be the lack of Arctic cold in the east, which I think folks will be thankful for, and the arrival of cooler, wetter weather to California and the rest of the West. And I think that's going to be generally beneficial after 30 to 45 days of dry and really warm weather in most places, with one of the worst snowpacks on record, if not the worst in some places. I'll get to that in a moment. So switching it up a bit. So it might make sense for me to bring up some data here on the screen. So I'm going to go share that now. You're going to see me in the corner before I head over here. This, once again, is the USDA NRCS live data viewer. It's actually a really, really nice tool. I hope it stays up online indefinitely to show real-time snowpack from all of the observing sites that exist in the western U.S. and also in western Canada as well. Actually, it looks like they've populated western Canada data as well. So British Columbia, you can get your numbers up there as well. There are some watersheds, of course, that include parts of Canada, those rivers that flow into the United States, which is why I believe that data is included here. But this is really what I want to show right now. I'm going to try and close crop this as best I can as I bring the drawing tool up on the screen here. But the main thing I want to point out is there's a whole lot of orange and red on this map. In fact, I think if I had to choose the most common color on this map, I think it's the dark red dots. And just to clarify, and I'm going to bring up my bright pink drawing tool because it's the biggest difference from everything else that's on screen here. We're talking about the entire Cascades and northern mountains of California. So the Shasta Mountains, the Cascades, Pacific Northwest, that entire region, all below 50% of average snowpack, in some cases well below. The Blue Mountains, eastern Oregon, all below. The Great Basin, essentially all of northern Nevada. The Wasatch, and the Central Rockies from north central Colorado into Utah. Southern Colorado, the watershed for the upper Rio Grande. Much of the Colorado Basin as well, all the way up into southwestern Wyoming. Upper Basin doing really poorly, a lot of places below 50%. Lower Basin doing even worse, almost everywhere below 50%. And then we go into California, where the farther north you go, the worse it gets. A lot of places now in the western slope of the Sierra, the Interstate 80 corridor, below 50% of average. And even at some lower elevation dots in the southern Sierra, we actually have individual observing sites that are below 50% of average as well. Although some very high elevation sites near Mount Whitney were still have above average, the legacy of those really wet October through December storms. They were warm, but they were also wet. So if you're up at 10,000 feet, it still fell snow. Similar story in the southern end of the Bitterroot Range up in Idaho, western Montana, where at lower elevations we're doing abysmally. We have below 50% of average in the lower areas, but there are some spots at high elevations that are near or even somewhat above average in the high peaks. But that's really the exception rather than the norm. In general, in this region here, snowpack is pretty abysmal. It's really, really low. And I think that can be illustrated just how dramatic that lack of snow can be illustrated in a couple of different ways, at basin scale and also by showing which locations are actually currently experiencing record low values for the period of record. So let me actually start with that latter point. All right, so as of today, every location that's got a red dot is experiencing its lowest snowpack in the entire period of record for that station as of February 8th. And again, there's at least 2 such sites in every single western state. So every single western state has at least 2 locations that are currently experiencing the lowest snowpack in the observed period of record for that station. And as you can see, in some areas like Utah and western Colorado, a majority of stations are experiencing record low. Now, if we extend this to this orange color here, which is the second lowest value on record, a great deal number more stations. So if you collectively say how many stations are experiencing either their single lowest or their second lowest February 8th snow water equivalent value on record, the answer is, in some states, it's most of the stations. And in many of the states, at lower elevations, there's record-breaking low values in many locations. In fact, even if we go up into some locations in southern British Columbia, this is near Kelowna at a lower elevation at 4,700 feet. We go to western Washington, the Cascades. We have, the red dots are everywhere, and they're throughout the West, all the way from Signal Peak, and that's at 8,300 feet. That's a high elevation site in southwestern New Mexico, to the southern Sierra. We have some periods, some stations here that are at low levels. A couple in the central Sierra that are at lower elevations generally, so where the snow line has been lower, and then just this pervasive picture. But maybe it's a little more obvious to see what's going on if I go to the basin conditions, and let me just switch over to a more color blindness friendly palette here. Also, I think it's a better scientific visualization. Anyway, when we have, this is just a brief science communication aside, by the way, when you have values centered on either 0 or 100% or some central value like this, as we do here, the normal value, the least interesting value, if you will, is probably 100% of average, exactly the usual amount of snow. So that should probably be a very boring color, like white on this map, for example. And you want a clear separation between values that are higher than usual, which would be blues, and values that are lower than usual, which would be red. So I like this color palette here. I'm glad the tool allows this. I kind of wish it used this color scheme as a default, but that's a conversation for another day. But anyway, it's a nice option to have, partly because it clearly depicts the starkness of the situation. Every single basin and subbasin in the western U.S. now has below average snowpack. Every single basin as of February 8th. Now, obviously, some basins are doing better than others. Up here is 97% of average, and there's the basin that includes Billings, Montana, is a lofty 90% of average, but those are the exceptions rather than the norm, because there are other basins that are, look at this, 17% of average. We're talking about 25 to 35% of average in a lot of key basins in the Colorado and in the Cascades. In fact, by this metric, the Oregon is doing maybe the worst of any single state except for maybe Arizona right now in terms of snowpack. So again, the Colorado Upper Basin region is doing a bit better, but even here now, snowpack has dropped well below average. But the lower basin in Colorado is doing, well, I'm overdrawing it a little bit, but anyway, is doing really poorly. You can see the gradient in the Sierra Nevada, where the southern Sierra is doing all right, 78% of average in the Tulare Basin, only half of average, though, in the San Joaquin Basin, and then only 40% of average in the Sacramento. We go north into the northern mountains, and we're actually only at 22% of average. The Sierra East Slope as maybe one of the other basins that doing just okay, because by virtue of its very high elevation, all the way up at 87%. But keep in mind, again, that these averages are relative to the last 30 years, or the 1991 through 2020 climate averaging period, which already incorporates some snowpack loss due to global warming that's occurred since the mid-20th century. So these are the deficits currently relative to our already climate-warmed normal, which is lower than it used to be. So when we hear about the crisis on the Colorado River system, that's relevant because, again, the Colorado River allocations were made back when stream flows were a lot higher than they were today, and back when we had a significantly cooler climate. So these numbers relative to when the Colorado Compact was signed would actually look even lower. But regardless, these are pretty alarmingly low numbers, and the worst of it is sort of in this swath from Oregon, including the far northern bits of California across the Great Basin into the central and southern Rockies and into the Four Corners region. And this is where I think some of the worst drought and wildfire related impacts will potentially unfold later this year, partly because this is the region that is least likely to recover its deficit, even though we do have a favorable pattern coming up where I think the upcoming pattern could push this region closer to 100% of average, could push the Southern Sierra closer to 100% of average. But this is the region where I think it's going to be pretty difficult for even the upcoming beneficial pattern to really move the needle. Because again, if you doubled the snowpack in some of these basins, you'd still be around 50% of average, which is still really, really low. But another interesting point I wanted to point out here is that if we look at a couple of other interesting statistics that can be gleaned here, let me just see what we've got. If we look at soil moisture right now, this is kind of interesting because except for the Front Range, the Rocky Mountain Front Range in New Mexico, Colorado, and Wyoming, in most places right now, the actual amount of soil moisture doesn't look too bad. In fact, in a number of places where the snowpack is record low, for example, in this basin or up here, soil moisture is actually a lot higher than usual. So what's going on here? Well, what's going on here is that in this swath, the snow that was on the ground has melted or fell as rain to begin with. So we don't have snow anymore, but at least the soil has soaked up some of that water. Now, the problem is, in a lot of these higher elevation locations, soil moisture in winter is usually really low because there's supposed to be a solid snowpack on top of that soil column that doesn't allow a lot of water infiltration into the soil during winter. So what's happening is the soil moisture is now above average for winter when it would normally be really low. It probably has values that are more typical of spring. Because what would happen in these regions is that you'd have snow melting in spring and early summer and replenishing soil moisture then. Instead, we're getting it replenished in the middle of winter. This is, in a sense, a zero-sum game because water that's coming from snowmelt today is water that won't come from snowmelt tomorrow. So if we have all this soil moisture now, it's nice to see at least that these numbers aren't terrible, although they're very bad in some other spots. And they're actually starting to dry out even in the Sacramento Basin, but not to extreme levels. But all of this high soil moisture now is not necessarily good news in terms of what might happen this spring and summer, because what it foretells is a really early loss of snowpack even in the middle of winter. This is all water that will start to evaporate once the conditions start to warm up, unless we can get a nice snowpack to sort of seal it in, and that would be helpful. So we'll see what happens there. But it's an interesting process. This does not necessarily mean that it's been extremely wet in this region. It just means that moisture that normally would have been locked into the snowpack has instead melted and is now entering the soil in the middle of winter when it normally would have taken until spring or summer to get to that point. And this is a screenshot that I of two plots that I put together. I'm going to make them big for the big screen here. I included these in the most recent Weather West blog post, which talks about a lot of what I'm going to talk about today in some slightly wordier detail. But the main point that I really want to emphasize is this. There we go. Just trying to find the right place for this toolbar. Choose bright yellow for this. The numbers from January are in. We're about a little over a week out. And so we now have the official stats for November through January 2026. So draw your attention first on the precipitation side. Again, these are all the western states. This is from the Western Regional Climate Center for the plots. I just put them on the same white page. But you can see that so far this winter it's been a mix of above average precipitation, particularly in southern and central California and southwestern Nevada, plus western Washington and some patches in the northern Rockies, and below average precipitation, which includes a bunch of western Oregon, but in particular Nevada, western Colorado and eastern Wyoming. So this region has been really hard hit because there's been both record warmth and in some cases near record or record dry conditions. That's why the snowpack here is just so absolutely terrible. But notice in northeastern California, for example, in parts of western Washington and parts of Idaho, western Wyoming, where that snowpack is really low, it hasn't been dry. It's actually been wetter than average in some of those regions. So what's going on there? Well, this is what's going on there. The story really is temperature, and everywhere that's in the bright orange color here experienced its singularly warmest start to the season on record. So the November through January 2026 period, the 3-month period beginning in November and ending just last week, every single location shaded in dark orange, which again is, the vast majority of the American West. I'm crudely drawing this here, but just to give a sense of what I'm talking about, that whole area, minus some small patches within it, was essentially record warm, plus some patches outside of there. But what's notable is that almost everywhere that didn't make it quite into the top warmest category still made it into the top 10 warmest, and in fact, in many of these locations, it was simply the second warmest on record. So I think it's probably correct to say that across 90 to 95+% of the West, this was either the record warmest or the second record warmest or the third record warmest on winter on record to date, although for most locations so far, this has been the single warmest period since at least 1895. It does not mean that 1895 was warmer, it just means that's when the period of record begins. So in at least in 130 years, or 131 years, I believe. So what's driving this record low snowpack? Well, in some places there is some low precipitation, but in most locations it's not record low precipitation. With a couple of exceptions, it's the record warmth. This is the main story. So is there a climate change story here? Yes, absolutely. No questions at all. We definitely have the climate change to blame for why this winter was as warm as it is. Is it the only reason why this winter was warm? No, definitely not. This is an extraordinarily warm winter that requires some combination of natural random variability of various weather factors plus this very prolonged, sustained, and intense winter warming trend that we've been seeing. That's the human-caused part of it. But if you ask what was the likelihood of seeing a winter as warm as the one we've been seeing so far without climate change, the answer is virtually zero. So is there a strong aspect of climate change? Did climate change essentially play a significant role in why this winter has been as warm as it is? Yes. Unambiguously, yes. It's increased the likelihood of seeing a winter this warm by many times. Probably the same thing is true of seeing snowpack as low as we're seeing this winter. And if we had had this precipitation distribution, for example, and temperatures closer to winter averages, many of these places would actually have near to above average snowpack instead of being near to actually achieving record low snowpack. So yes, it absolutely makes a big difference. And when I say it was record warm, again, that's not a figure of speech as a climate scientist. It means it's the number one rank in over 100 years, in the full period for which we have records. I did want to point out that when we talk about snowpack, we don't have a 130-year record of snowpack. In fact, in some of those locations, the snowpack records technically only go back 30 to 50 years. So it's not quite the same. We can't quite make the same bold claims about it being the lowest in 100+ years in terms of snowpack. In fact, there's some locations probably that did see maybe in the 76, 77 winter, maybe comparably low or even maybe slightly lower snowpack, although I also think there's some locations that are legitimately lower this year. Worth noting that this is not, in general, a record-breaking low snowpack in California, mainly because it's actually been wetter than average. We've had above average precipitation so far this season in the Sierra, despite having that record warmth. So in order to get a record low snowpack in the Sierra, we kind of need both low precipitation and extremely high temperatures as well. But in general, this is a winter of superlatives in the West, but the real superlatives is the temperature-related one, which has obvious links to climate change. And I'm actually a little bit bewildered by how many folks, including journalists, who have reached out and said, wait, this can be connected to climate change. I thought it was, we can't connect these individual weather events to climate change. And I think, first of all, the seasonal scale of warmth, it's not exactly an individual weather event unto itself to begin with. But the broader point holds: single individual events in general do not a climate make. But the problem is it does exist in the context of all the trends that have come before. And we know that the robust winter warming trends that we've been seeing, this is very much consistent with the trend that is, in fact, human caused. And so we know that when we see record-breaking extreme warmth, that climate change has greatly increased the odds that record-breaking extreme warmth occurred, and also substantially boosted the actual magnitude of the warmth that's occurred as well. We've sort of reached the point in climate science where we don't need an individual study for each particular extreme heat event to make that qualitative determination. Now, exactly how much of this anomalous extreme warmth is due to climate change as opposed to other factors, that would require a nuanced study that would take some time to do. But the reality is, I can say with confidence that it's extraordinarily unlikely that we would have seen a winter as warm as this one, or had winter snowpack as of present that's as low as it currently is, were it not for the human-caused warming that we've seen so far. All right, so that's the state of where we are now, but what's coming next, which is why I suspect many of you are on here today. And let's bring it over to satellite. So here's a live from space view. It never ceases to amaze me that we can get this data piped directly to my computer and then me rebroadcasting it out to the interwebs in real time. But these are images in near real time from space, and this is a pretty cool satellite picture. This is from the Goes West satellite. Just for orientation, I'm very crudely outlining California with the tool. You can see that there's that blue outline there. So the west coast, of course, is here. And you can see on this map, there's a few features of pretty cool interest. One is there's an obvious low pressure system out here. So this is tomorrow's system starting to spin up. You can see the cyclonic, or counterclockwise, flow around this low pressure system, as you will find in all low pressure systems in the northern hemisphere anyway. Excuse me, just took a sip of some water there. What you can see aside from this low pressure system are a couple of other little interesting features. You can see this sort of, well, actually, let me get to that later. We can see a developing baroclinic leaf cloud in this region here. So this is the baroclinic leaf, which is not a particularly threatening weather feature, to be clear, but it's a pretty classic mid-latitude weather system type feature when you have a strengthening low pressure system where you have upward motion going on in this region. So you have upward moving air in this region that is denoted by the baroclinic leaf here. Upward motion in the atmosphere means you have eventually you have cooling of the air, and you have condensation of that air once it cools to its dew point, and the formation of clouds, and eventually precipitation when that process continues. So this is the portion of the system. You can kind of, I don't know exactly where it is, but I'm kind of just drawing in an idealized form here because this is such a pretty satellite picture. I'll restart it. So here's the low pressure system. The developing cold front is probably somewhere in this region here, so I'm going to draw that again poorly as usual. And then there's somewhere in here is some semblance of a warm front, probably. That would be my guess. It's somewhere in there. So you have warmer, moister air surging northward here, and colder, drier air coming down behind it here. So this is kind of the classic mid-latitude cyclone feature here, and this baroclinic leaf is kind of developing right along that kink in the flow, that upward moving air contributed both by the warm front up here and then sort of by the combination of the lift from the cold front and the warm front down here. So something like that. And so the other interesting feature, if you see this sort of this linear cloud feature right here, these are cirrus clouds, but you see this little, this is interesting, this little sawtooth pattern in these clouds right here. This is just sort of a meteorological curiosity. You might notice that sort of sawtooth pattern. It almost looks like saw blades moving. This is because there's a jet streak. So the jet stream is quote unquote rounding the base of the trough, something like this. So just imagine that this is the river of high velocity air at the upper atmosphere that makes up the jet stream. And imagine that in this region, sort of where the streaks are occurring, so sort of in this general vicinity, that the jet stream is stronger than it is elsewhere. So here it's sort of plus, plus, and then over here it's kind of minus, minus. So you have a jet streak. You have stronger air movement converging into the jet streak and then slowing down as it exits. This is sort of indication that there's some turbulence at the jet stream level, and that strong jet stream is kind of causing the fluid flow to trip over itself. So it's kind of bumping around. So if you were flying through this, if you were flying from, I don't know, SFO to Hawaii or something, I have a good feeling you'd probably have the seatbelt signs on, even at cruising altitude here, because this is the kind of pattern where you might get some bumps at 30,000 feet. But in general, a nice, pretty low pressure system, and there's finally something to look at on the satellite other than clear skies and some Central Valley fog. By the way, that fog has finally cleared out of most of the Central Valley today, just in time for the clouds to come back from this low pressure system. Tomorrow, it looks like this low will move pretty much directly towards San Francisco, make landfall in the Bay Area as a slowly strengthening, but nonetheless strengthening system. And I always sort of give strengthening systems a half category bump in their impacts or something like that qualitatively above the sort of the standard weight. They sort of punch above their weight, if you will, as opposed to similar strength but weakening systems, which may sound obvious, but I think it has to do something with the fact that when you're strengthening, you tend to get these bubbly convective clouds more readily because of that upward vertical motion than when a system is weakening, because then you kind of put a lid on it, you get some downward motion. And even though the low might look strong, you kind of lose these clouds. With this one, it's going to strengthen slightly as it moves towards the Bay Area. Doesn't look like an extreme wind event, extreme rain event, but a moderate wind, moderate rain, and there could be some thunderstorms because, and I'll point this out in a moment, along the coast of the US, of California actually, the water temperatures are ridiculously warm. In fact, let me show that briefly. I'm going to go back. This is a blog post. I have this image in my blog post as well. I'm actually going to refer back to Weather West. Here we go. So this is from February 6th. It's a couple days old, but the general picture hasn't changed. This is from NOAA's heatwave, California blob heatwave watch page. There's a link in my blog post. You can go to weatherwest.com and find the direct link. But the main thing I wanted to point out is that this is degrees Celsius warmer than usual. Look at the extent of the warm temperature anomalies all up and down the West Coast. We're talking about 2 or 3 degrees Celsius, so up to 5 or 6 degrees Fahrenheit warmer than usual. And keep in mind that the amount of energy it takes to heat a given mass of water is 4 times the amount of energy that it takes to heat the equivalent mass of air, or if you're speaking in terms of volume, because of course air is much less dense and therefore is more voluminous than water, 3,000 times as much energy to heat the same amount of water as the same amount of air. So the point being, it takes a whole heck of a lot of energy to heat the entire nearshore water by 2 to 5 degrees Fahrenheit, locally 6 degrees. So there's a marine heat wave. In fact, NOAA officially says that any area within the black contour here is experiencing a notable marine heat wave. Again, that extends all the way from central Baja California, all the way up the entire California, Oregon, Washington, and British Columbia coast, all the way up to, if I hide this tool, all the way up to southeastern Alaska. So a pretty extreme marine heat wave has now developed. This is going to affect incoming systems because it's going to give this guy a little more juice, a little more fuel. How does it do so? Well, if you have a marine heat wave in this region here, as the system moves ashore, it's going to do a couple of things for us. One is it's going to add more moisture to the air, what's known as the boundary layers, the lowest level of the atmosphere, as the storm moves on shore. So it might boost the amount of moisture in the air, boost rainfall rates right along the immediate coast when it moves inland, just by virtue of there being about 3 or 4% more moisture in the air immediately above the ocean than 3 or 4 times 3 or 4, because that's about how much warmer the ocean is in degrees Fahrenheit. Well, that's 9 to 16%, and that ain't nothing, as they say. That's a substantial additional boost to the amount of moisture that's available to any given storm, like the one we're going to see tomorrow or over the coming days. But the other thing it does is a little less obvious, but is sometimes more consequential. It can also destabilize the atmosphere in a storm like this as it moves over the warm waters, meaning that it can actually result in an atmosphere that it has a greater propensity to have upward motion in the first place, by virtue of the fact that in the lowest part of the atmosphere, you're adding both moisture and warmer temperatures. So if you want to make air more buoyant, make it easier to rise, and therefore produce precipitation and clouds, you want it to be as buoyant as possible in the lower levels. So you want it to be warmer and moister. So a warmer, moister nearshore ocean actually gives you both. It doesn't just give you more moisture, but it also raises the temperature of the air near the surface of the ocean by at least a couple of degrees as well. So here you got warmer, moister air, and you got an incoming storm system that wants to lift that now more buoyant surface air upward vertically. And the net effect is that it somewhat increases the chance that you get these bubbly convective clouds, like the ones we're seeing here, these showers and thunderstorms, these towering cumulus and cumulonimbus clouds, including some lightning potentially. And it means that all of these inbound storms over California will have a somewhat increased possibility of producing these localized torrential downpours and some isolated thunderstorms. So there's actually a decent chance of some lightning in the coming days throughout much of California. This is partially contributed by the cold, dry air coming in from the northwest associated with these systems aloft. It's partly associated with this jet streak, which is offering some upper-level support, some upper-level lifting mechanism. It's partly associated with the low-pressure system itself, which induces upward vertical motion in its right front kind of quadrant here on the eastern side. But it's also going to be enhanced by this increased moisture and temperature of the boundary layer, and therefore its decrease in stability, or contrarily, increase in instability that we're going to see. So I would not be surprised if we see yet more increased prevalence of heavy localized downpours and thunderstorms, both with this system and with ones to follow in the coming days. The other thing I think might happen is that the models might be slightly underestimating snow levels. And so the snow levels could come in several hundred feet to 1,000 feet, maybe higher than expected in the Sierra, because they don't always fully capture the entrainment of warm, moist air. Some of the water that falls as snow near Lake Tahoe, for example, is actually coming from surface moisture that comes through the Golden Gate Gap and then through the Carquinez Strait and up the I-80 corridor. So actually following the route that you might take if you were going on a ski trip from San Francisco along Interstate 80. If the water in the nearshore waters and in San Francisco Bay is warmer than average, well, then the path it's going to take is going to bring that warmer, moister air to the Sierra. So you're still going to get snow at higher elevations, but I wouldn't be surprised if the snow levels end up a little bit higher, at least initially, with all of these storms than is initially predicted by models. And if snow ratios are a little bit lower than expected. Not necessarily less snow water equivalent. In fact, that actually might be boosted a little bit at higher elevations, like at 7,000 and 8,000 and 9,000 feet, because of that extra moisture. But you might have to go a bit higher up the mountain to get to the snow line than some of the models are currently suggesting. So with that out of the way, let's look at what some of the actual forecasts are looking like here. And I'll pull this up. Let's get to the western U.S. Now, and let's just use the European model, which is often the best single one to take a look at. Here is essentially right now, we have that low pressure system west of California down here. That's what we're talking about. And as I step forward through time, as I mentioned, this is going to essentially make landfall. So actually, today's forecast is a little bit different from yesterday. I haven't looked at it since last night. This one looks like it's closer to a Monterey Bay landfall. than San Francisco. But in any case, it's San Francisco, Bay Area, Monterey Bay Area. That's the general part of California this thing's going to make landfall. And it will do so going into tomorrow. So we're going to see this precipitation increasing as the day goes on. So this is sort of tomorrow morning, the rain begins, and as we go into the afternoon, early evening tomorrow is when the heavier rain and some wind will probably arrive on the central coast and the Bay Area. And we will also get some decent precipitation even down into the central coast and even LA County. Rain totals are going to tail off pretty quickly once you get south of Los Angeles, so Orange County, San Diego. See a little bit of rain, but not too much. But it looks like a decent little storm for the central coast, and it will bring some Sierra snowfall. But one thing I want to point out is that snow levels will start really high. This time tomorrow, I would expect it to be raining at Lake Tahoe. Yes, once again, rain at Lake Tahoe. At this point, there's not really much snow left to melt at lake level, so be that as it may. And even into tomorrow evening, snow levels will fall, but it might take a little while, as I mentioned, with that warmer marine air coming in from that marine heat wave. I think it'll take a little longer than the models initially suggest for snow to fall to pass and lake level, but it will eventually get there. There is cold air behind the front here, which is the good news, so I would expect snow to begin to fall down to lake level and probably below that as we get into Wednesday. Not super low snow levels, though. This is still a storm that's on the warmer side, but there will be some higher Sierra snow. It just won't be a great snowmaker. This system, by the way, will kind of fall apart a bit as it goes in. There'll be some snow across the central Rockies, but really this is not a big snowmaker. This is not if this were the only system we were going to be getting in the next couple of weeks, let's just say, I would not be nearly enthusiastic about this pattern change. The other thing that's notable about tomorrow is low. It will stall out still near San Francisco, hang out near the Bay Area into early Wednesday, and there will be rounds of showers and possibly thunderstorms as relatively cold air aloft sits over these warm coastal waters. So if I look at I'll look at that in a different model in a moment, actually. So this system will kick itself. It's not going to go anywhere quickly. In fact, showers and scattered thunderstorms could linger through much of Wednesday before finally kind of moving out of here. The storm is just kind of fall apart by Thursday. Things will dry out. Things will get sunny again. It'll even be relatively warm again. As I mentioned, if that were the only system, we'd be in trouble. But it does look like thereafter more significant systems. This could be about a week out. So we get the initial point of entry, a weak to moderate, and relatively warm system. We might get some much more active weather though after that. This is one depiction of what could be a very good snowmaker for the Sierra Nevada and for a good portion of the interior West. Storm after storm as we go toward mid and late February. So a significant pattern change, much needed. This is just one model's representation. So let's look at the broader ensemble here at the total accumulated precipitation. So with this week's system, some decent rain in California, but not much elsewhere. This really is a central California system into LA County at the far southern end. Things dry out again a little bit thereafter, but then as we get toward mid-month, really wet conditions potentially taking hold across a good chunk of California. And then critically, and this is what I'm glad to see, some blues, even some light purples across the Intermountain West and the Cascades. This is what we like to see at this point after a really dry 30-40 day period. But even more consequential is, as I mentioned, we're starting out warmer than average. Here's how the storm's going to start out. California, again, a couple more days of much warmer, above average temperatures, and this is true in the interior West. It's still really warm going into Wednesday, Thursday. Things remaining and maybe even warming up again next weekend, above average. Not exactly what we wanted to see then, but then we get toward later in the month, and we actually see a higher likelihood of a more widespread cool down. This doesn't look like any kind of Arctic outbreak by any means, but we got rid of the reds. This is what we wanted to see. If we want real snowpack accumulation, we got to see temperatures cool well below their current levels, and that is what appears to be in the cards for the second half of February across the West. So the combination of this near or below average temperature second half of the month, plus this, which is near or above average precipitation, certainly for California, and then you can see there's some patches of it inland. It isn't gonna completely turn the tide on the incredible snow drought over here, but it might do a number on the deficit we have in the Sierra if things come together. I'm a little bit concerned it might not get as cold as some of the models are suggesting, because I think they're underestimating the influence of this extreme marine heat wave in this region. And so, of course, all of these storms got to come and blow that Pacific moisture inland. Even that said, I think the higher elevations are probably going to do pretty well with snow, and at least in this pattern, even the lower elevations will be getting rain, so it won't be dry in the same sense. The other point I wanted to make here before I swap over to the questions is that the broader pattern over North America is going to be a reversal of the recent actually, let me pull up the current non-5-day map just so we can see it better. Here we go. So the warm west, cool east pattern. So here's the warm west we've been getting. Here's the cool east. The contrast between warm west and cool east has been extraordinary. Watch what happens as we go through the month. Watch this kind of reverse itself. A little bit indistinct, but then it's going to start to become more apparent. Here we go. So as we get toward mid-month, here's the reversal. Cool west, warm east. I think a lot of folks will like to see it. But the other thing that's going to be interesting is we start to see the rise of this Aleutian or Bering Sea blocking ridge, and that becomes really a persistent feature moving toward later in the month. So what's going to happen with this is we may see a pool of really cold air building across Western Canada. This is what's known as a locked and loaded pattern by some, in the sense that this really cold reservoir of air up here has a propensity to spill southward and eastward. So this could result in another really cold episode in the eastern US later in the winter. So as you go into late February, early March, there's a slight chance it could take a more circuitous path and actually bring some really cold air to the west. But right now, I'm not seeing that in the next couple of weeks. This is probably at least a couple of weeks out. So the question is, there's a pretty high confidence that this blocking ridge will build up a nice big cold pool up here, but where's it going to go? Will it remain sort of locked up in Western Canada, or will it spill southeastward and bring another warm west, cold east pattern? That wouldn't be good for snowpack, but if it actually manages to spill west over the Intermountain West, that could actually be a sort of a snowpack saver. Could contribute to a miracle March. So I'm not going to bank on that because we don't know what's going to happen yet, but that's an interesting accumulation of cold air up there. Could have some interesting impacts down the line. Last thing I wanted to point out was if I hop over here, I gotta sign in here to this to show you the part that I actually wanted to show you, which is we go over to the convection allowing, or even actually let me just hop over to the European model. I don't even need to show that. Here we go. This is what happens when you do it live. Just want to show in general, if I zoom in on the Western US, let's do that. Here we go. Here's California. That's a little bit confusing. Let me just see most unstable CAPE. Let's just have that on here. As I toggle through, what you can see is that this is a measure of the convective available potential energy, or CAPE. Also a measure, think of it kind of as a thunderstorm potential energy. Anytime you see a number that's noticeably above 0 in California, it's a little, especially this time of year, it's a bit unusual. So we have values in the 2 to 5 or 600 joules per kilogram range with the system this week in Central California. This is indicative of the potential for thunderstorms from about LA County northward into the Bay Area and the Sacramento Valley. Not seeing super high risk of severe weather right now, although, you know, in these kinds of patterns, an isolated cell could always pop up. And just the general risk of some thunderstorm activity. We actually see this with both this system and then again with, I need to go to an earlier model run here. Here we go. Subsequent systems, as I mentioned, cold air aloft, warm ocean at the surface, most of these generate some noticeable cape somewhere over California, so a higher than usual chance of thunderstorms with these systems. All right, so let me pull back. I'm going to go back full screen, so you'll see me. I'm going to answer some questions. First, a comment, and I'm going to pin this message to the top of the chat in case anyone lost it. But what I've got for you here is a link to my talk at the Aquarium of the Pacific in Long Beach last week. I met some of you in person, so it was nice to see some folks IRL, as they say. But if you did miss it, it was also live streamed, freely available to everybody, but it was also recorded, and so now is available to everybody who was not able to join, even via the live stream. That link is pinned at the top. It's an overview of what we expect with water and weather extremes in a warming California. And if you're really a bit of a weather or climate or water nerd, I would count myself as all of the above, check out the live Q&A session I had afterward as well. There were some really good questions, and you'll hear some answers that are maybe a little bit more nuanced than what you get in some of my more standardized public presentations. So do check out that link. The whole talk plus the Q&A session afterward, I believe, was recorded and is archived on YouTube on the Aquarium of the Pacific's webpage up there, linked at the top of the live chat right now. As a comment from Spence that the presentation at the aquarium was excellent. Thank you, and I'm glad that the link is now available to everybody else. A comment from Matthew that I think I addressed, but good intuition there. Hi Daniel, with all the cold troughing we'll be seeing the next 2 weeks, could the warm water off the coast make for some intense thunderstorms up and down the whole west coast? It might be a bit much to say intense thunderstorms up and down the whole west coast, but I do think that the current marine heat wave increases the odds of heavy coastal downpours associated with storms that do move in, and in cases where we have cold air aloft moving over unusually warm oceans that have been warming and moistening the boundary layer, making it less stable, yes, I do think it increases the odds of thunderstorms. And if ambient environmental conditions like additional lift from a low pressure system or wind shear, which is required for strong to severe thunderstorms, we need that rotation in the atmosphere. If those ingredients do come together during any of these systems, it doesn't really look like they will so much with the first one on Wednesday this week in California, but they could with subsequent systems. Yes, I think, and also notably, seasonal models predict this marine heat wave to continue straight through the spring and into the early summer. So could there be some additional episodes of thunderstorm activity with springtime systems this year if we get cold air aloft? And could that lead to some severe thunderstorms in unusual places near the west coast later this spring? Is an interesting question. Maybe, we'll see. Ronster asks, would a strong El Nino result in an even more extreme record cold in the east versus record warm in the west situation? Not necessarily. One of the reasons why we have this really warm west, cool east amplified wavy jet stream pattern is because the tropospheric polar vortex, this concentric bands of west to east blowing winds that sort of act like a fence and keep cold air trapped up in the Arctic, but occasionally that fence weakens and the vortex either becomes displaced or stretched or broken up, as has been the case in recent weeks, allowing these really weird looking lobes of cold air to infiltrate over the portions of certain continents in the northern hemisphere. That's the proximal cause for the contrast between the record warmth in the west and the record cold. I should say the record warmth in the west and the extreme cold in the east. In most cases, again, not record-breaking to nearly the same extent that the western warmth has been record-breaking in its own right. With an El Nino event, there are interactions between the tropics, which is where El Nino unfolds, and the Arctic troposphere-stratosphere interactions. The answer is it's complicated. It depends on other things. And it's actually not so much a pattern we would as likely see during a strong El Nino event, because a strong El Nino event favors a strong zonal jet stream all the way from the eastern Pacific across the southern tier of the U.S. So actually that strong jet stream is kind of the opposite of the condition that you need for a really wavy jet stream. Usually the stronger the jet, the more linear it is. And so a strong El Nino, this is the reason why there is, yes, I promise there still is a relationship between an increased likelihood of a wet winter in Southern California during a strong El Nino event is mainly because of the influence that it exerts on making that Pacific jet stronger and more eastward extended. So the opposite of the condition that you'd need for a really pronounced wave pattern over North America. So I guess the answer is no, but also we can't really get temperatures much more extreme cold than we've seen in the eastern US anymore in our warmed climate. We used to be able to. In fact, there are a number of events in the 20th century that were colder than the events we saw in the eastern US over the past couple of weeks. But, you know, the fact that the eastern US has been as extremely cold as it has been is actually a testament to the fact that we're kind of scraping the bottom of the barrel in a sense. I'm not sure that we can get temperatures much colder than that anymore in the eastern US because the source region in the Arctic where that cold air has to come from simply isn't as cold as it used to be. Keep in mind that the Arctic is warming about 3 times faster than the rest of the world. So you take that global average number and you multiply it by 3, and that's how much the Arctic has warmed. So if we've warmed, by several degrees Fahrenheit in many places over land on Earth, the number is a lot higher in the Arctic where all that cold air has to come from. So probably no during El Nino because of the fact we get that stronger west to east jet pattern and not this wavy north to south in the center of the continent pattern, but also because in a warming world, I just don't think we can get temperatures much colder in the eastern US than we've recently been seeing. So it's really just a testament to how much it's already warmed in that sense. Is the Pacific Decadal Oscillation moving into a warm phase? Asks Tim. Maybe, because we certainly see a different prediction for this year than other recent El Nino events, where it actually looks like the entire North Pacific looks really warm, including the California coast, in terms of ocean temperatures. We haven't seen that pronounced pattern so much in recent years. So, the decadal oscillation is, well, decadal, so it's something that you can really only calculate somewhat in retrospect. But are we moving in a direction away from a persistently negative PDO? We'll see. But there are some hints that this year is going to, especially with the developing and yes, potentially strong, at least initial indications are subject to high uncertainty. So don't quote me on that one. But that's the insider scoop, is it is looking more and more likely of an El Nino of significance. Let's just call it that for now. With each passing month, the models are getting more aggressive with their prediction for what things could look like come June or July. So for now, let's wait and see, but I'm increasingly thinking that the later in the spring and the summer months in California might be dominated by the early stages of a notably strong El Nino event. That is my current hunch. We'll see where we get in the months to come. Question from Rachel. Would it be helpful to create basins where extra rainfall could penetrate into the paleo valleys of California? The water table is very depleted, reservoirs don't hold enough water. Or whiplash weather? Well, the short answer is yes. This is known as a groundwater recharge, and there are in California some regions of dedicated recharge for groundwater in places where the subsurface geology is favorable for it. You can't just do it anywhere. Some places you can let water sit and it won't really soak in. But other places, yes, you can do this. And this is actually something that a number of environmental and water management agencies are starting to move toward as a good potential use of land and space in a warming climate to ensure water resilience. In fact, there's even some efforts now to connect rivers with their floodplains, partly so that those floodplains can serve as those recharge basins. So in some cases, this is sort of a highly engineered system where you pump water from point A to point B and dump it somewhere where it can soak in. That's one version of this. The other version of this is to say, well, when the river is already flowing high, let's just let the river flood in a controlled way in places that we've designated as recharge basins. So flood mediated aquifer recharge. FLOODMAR is the acronym, and this is something that California is really thinking about implementing at a larger scale. You can add yet another acronym to it and call it FIRO-FLOODMAR, FIRO coming from Forecast Informed Reservoir Operations, And this is essentially saying that we actually have knowledge of the weather that's going to happen over the next week. We shouldn't pretend that we always need to operate reservoirs as if, a record-breaking storm could arrive at any moment, because, well, they could happen in any given month, but we generally have at least a week or two of warning for them. And so we can plan accordingly. We can adjust how we operate critical water infrastructure to accommodate the fact that we have pretty good weather forecasts today that didn't exist 50 to 70 years ago when some of these system operations were originally developed. And that can allow us to potentially maintain our resilience against floods, but also conserve more water in reservoirs, and then also strategically release water from reservoirs in advance of storms so that they can be allocated to these groundwater recharge basins. So that is one option, especially in northern and central California, the Central Valley, the San Joaquin, Sacramento, Tulare basins. In a more urbanized setting like, say, LA County, there are still recharge basins within LA County, within the urban context, and they're smaller in scope and in scale, but they're still useful. Believe it or not, even on a very micro scale, some of these new urban street projects you see in the city of LA have what are known as bioswales, and these are sort of those really small, like the micro parks that you might see on roadway medians or things like that, that can offer some ability for groundwater to permeate. Instead of having a contiguous asphalt or concrete surface, you have interrupted that surface, and you've put in things like sand and rocks and plants in the medians, on the margins of sidewalks and roadways, and in between buildings and people's yards, and up against the adjacent to parks and things like that, to let the water soak into the ground. There are some issues with pollution, obviously, especially in an urban context. You can imagine if you have water running off of a street with the buildup of oil and stuff on it, that it gets a little bit tricky having that run directly into groundwater aquifers. So there are pollution issues too. But the short answer is that that's a very rich topic for further exploration. Maybe a good topic for a conversation another day. But the short answer is yes. This is something that can be done. It's something that is increasingly being done at a larger scale. And it is something that California is actually taking the lead on in recent years. Matthew mentions, I think probably with respect to the magnitude of the ongoing snow drought, that climate change is a factor, but things like the QBO, meaning the quasi-biennial oscillation, and the MJO, another three-letter meteorological acronym, the Madden-Julian oscillation. The QBO, by the way, being the quasi-biennial oscillation, meaning a quasi-2-year oscillation in the stratospheric wind patterns, the west versus east winds in the stratosphere. They actually completely reverse direction every couple of years, which is a really fascinating aspect of planetary dynamics that I don't even think I was very aware of into the past 5 or 10 years. It turns out it interacts with things like El Nino and La Nina and other things to produce very different impacts. And also interacts with the Madden-Julian oscillation, or the MJO, which is a tropical mode of variability. This is something that unfolds every year. Usually there's multiple cycles of the MJO in any given winter, essentially describing the relative longitudinal location of clusters of tropical thunderstorms as they wiggle back and forth across the Pacific. And it matters for California and North America because it affects sort of where the jet stream ends up, how strong it is, and where the wiggles in it go. That's the very short, very quick version of all of this. So essentially, yes, you're right. I mean, those are other influential factors in explaining why it's been as warm as it has been, and in particular why the precipitation has been doing what it's doing. But the real question is, what is the most fundamental aspect of this winter? Like, what's the number one most notable piece of it? And it is the literally record-breaking warmth. Not just that it's warmer than usual, but that it has literally been the warmest start to the winter on record for almost the entire West. And the reality is that, yes, there's always contributions from various natural oscillations in the atmosphere, although it is also worth noting that climate change is also affecting things like ENSO and the Madden-Julian oscillation. They are no longer fully independent of the changing climate itself. But they are still primarily natural oscillations that existed and continue to exist, even absent climate change. But the question is, how did we get all the way up to record warm? And that would have been almost impossible without the global warming we've seen and the regional warming we've seen to date. So it's always a confluence of factors. It's never just any one thing. There's always some natural factors at play. But the climate change piece of it isn't small anymore. I mean, it's just, and I think people are often surprised when we crunch the numbers and show just how large a role it has played in some of these warm temperature anomalies, or these record-breaking heat events, or these record low snow events, or record high rain events. It's not a tiny number. It's a substantial part of the total in some cases, even though there is always also a contribution from the natural variability, and in some cases, natural variability. You know, if you have a heat wave, for example, that's 20 degrees Fahrenheit above average, it's probably the case that the non-climate change part of it got you maybe 3/4 of the magnitude of that heat wave. So I don't know, maybe 15 degrees out of that 20 degrees was would have occurred even if the climate hadn't warmed. But yeah, that's still a pretty big number at the top. And as it turns out, it's that last 5 degrees that matters the most. Think about snow in particular. It's actually even more obvious why that extra 4 or 5 degrees of warming matters. Because imagine if you had the same weather pattern as we had this winter, but it was about, let's be even stingier with the climate change attribution. Let's just call it 3 degrees Fahrenheit. How many times this winter has it been raining at 33 degrees or 34 degrees in parts of the Mountain West, whereas with 3 degrees cooler temperatures, it would have been snowing at 31 degrees? The answer is in quite a lot of places, quite a lot of the time. And so that's one illustration of how, even if we say that the magnitude of the anomalous warmth is maybe only, 15, 20, 25% due to the long-term warming trend, it actually has a huge impact on why we see snowpack as low as we've seen this winter. Another bonus of the incoming weather is it will clear out, as Spence mentions, the bad air quality. That is always a nice benefit of low pressure and precipitation and wind. It does a great job at improving air quality, so that's absolutely true. BB SoCal asks, what will the initial snow levels be in SoCal? It looks like snow levels will be above the levels of SoCal. It does for this initial storm, at least as far as I'm seeing, it looks like it's going to be pretty darn warm, and it's going to be amplified by the really anomalous warmth of the ocean offshore. So first storm, I don't really think is going to produce meaningful snowfall in the mountains of Southern California. Subsequent storms during the cycle very well could, though, so that's a bit of a different question. All right, so there's some other good questions that I might have to hold for the next time, just since we've gotten some bonus time. But just trying to see if there's any other week-specific questions here. Okay, I think we've reached the end of the Q&A portion of today, so I just wanted to thank everybody again for joining me today, and encourage folks who do appreciate these live streams to sign up to receive notifications that these live streams are going to occur. I always do post them across various social media platforms as an announcement, so if you follow me there, you'll see it. But the more direct way is to subscribe to this channel, which, yes, I feel obligated by the algorithm to mention that at least once every session while people are still paying attention. So thanks to the now nearly 20,000 of you who have already done so. But also separately, you can turn on notifications for live streams, and that is a separate step from subscribing to the channel, which is, I know, a little bit of a pain, but if you want to be notified when these are going live, that is probably the most efficient way to do it. But you can also keep an eye on your favorite social media channel. I am on most of them, and also, you can subscribe to the Weather West blog. I know this is an option that I guess a lot of folks weren't aware of. To be fair, it is a little bit of a hidden link. But if you go to weatherwest.com, I want to be notified when I have new blog posts. You'll get an email. And I did, by the way, for those who experienced a problem with last month's newsletter email, I've fixed that with the most recent one. I'm happy to say. There's a link on the right sidebar of the page where you can just fill in your email, push submit, and you'll be subscribed. You do have to click the confirmation link that arrives in your email inbox, but that's the full process. It's all free, it's all open to everybody. Just a nice way to be reminded when those blog posts come out. And I do often, when I have a live stream scheduled during major events, also now mention that in the blog post itself. So trying to make it as easy as possible for people to know when I'm going live and to join me in those moments. Sometimes on short notice, sometimes with at least a couple days of notice, sometimes in between. I am going to, by the way, work on this year trying to expand to some other times and think about having a semi-recurring window that I'll use unless there is something urgent going on. So it might be a little bit easier for people to plan on that. So stay tuned. One challenge is my schedule varies a lot from week to week, so it's hard to find a consistent window, but I might try and give that a go. Might offer a survey at some point soon to figure out what time would work for the most people. So stay tuned for that one. I know there's not one time that's going to work for everybody, but the other good news is that these sessions are always recorded, including this one, and you can always go and view it asynchronously after the fact once the video uploads, which will happen relatively soon after I push the end button, which is what I'm about to do now. Thanks for joining, and see you next time.